Hi everybody, this is a lecture on section 6.1 on power series. So a power series is a function b of x defined as a polynomial of infinite degree. So when you write it like this, so sum n equals 0 to infinity a n, which is a constant, x to the n, you call that a power series centered at c equal to 0. And you could also have a power series centered somewhere else, a n x minus c to the n. That's a power series centered at c. Right? And, for example, hold on, before that, the interval of convergence of a power series is an interval a to b, or a to b, or a to b, or a to b, right? So, interval from a to b, and you can, or where either you do not or do include each endpoint. So there's 4 possibilities. Where the power series converges absolutely, in its interior. So within the interval, the power series converges absolutely. Outside that interval, not outside, on the boundary, it could be conditional convergence, could be absolute convergence, we don't know what, but outside the interval, power series diverges. Okay. So let's take an example. Interval convergence power series is an interval, blah, 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 centered at C, which might be 0 or might not be 0. Where the power series converges absolutely in the interior and and outside the interval diverges. So let's take an example. So find the interval of convergence for the power series P of x equal to the sum n equals 1 to infinity 1 over n2 to the n x minus 5 to the n. So this is a power series centered at 5. Okay. So one other note before we do that. Okay, the interval of convergence is always centered at C. That is, b plus a over 2 is equal to C, where a and b are the endpoints of that interval. Okay, so that's always the case. All right. So let's find the interval of convergence for this power series here. Well, by the ratio test, P of x will converge absolutely when, right, the limit as n goes to infinity of the absolute value of an plus 1 over an is less than 1. Okay, so we just want to look at this limit and then see when it's less than 1. So an plus 1 over an. Now here, be very careful with the absolute values, and I'll show you some of the things you got to watch out for. Okay, an plus 1 is 1 over n plus 1. 2 to the n plus 1. X minus 5 to the n plus 1. Over 1 over n 2 to the n. X minus 5 to the n. Okay, all of this stuff here is positive, but the x minus 5 need not be. Okay, because x could be less than 5, in which case x minus 5 need not be positive or negative. So how do we handle this? Well, all the expressions that don't use the x's, that just use n's, well, you know if they're positive or negative. The n is always positive. Right, the n's are always positive, and then, you know, whatever function you have in terms of n, you can see whether it's positive or negative, and then just omit those negative aspects to it, or make it positive in some way. So here we have this, right? And then here, x minus 5 to the n cancels into x minus 5 to the n plus 1. But we have to keep that in absolute values. So something to remember. The absolute value of a times b is absolute a, absolute b. Right? So the absolute value of this whole thing is the absolute value of this stuff, which is positive already, so I don't need it, times the absolute value of the x minus 5. Okay? And we don't know if x minus 5 is positive or negative, so that absolute value has to stay there. All right. Here, the 2 to the n and the 2 to the n plus 1 cancel like that. So we're left with the limit as n goes to infinity, n over n plus 1 times a half times x minus 5. And as n goes to infinity, this is 1. And then this is a half, and this is x minus 5. Remember, n is going to infinity, not x. Okay, x is different than n. So x is just sitting there as n moves to infinity. So this limit, as n goes to infinity, this bit is 1, this bit is a half, this bit is x minus 5. And you want that to be less than 1 for absolute convergence. Right? So p of x converges absolutely when absolute value x minus 5 is less than, well, when 1/2 absolute value x minus 5 is less than 1, that is when x minus 5 is less than 2. Right? So this number here is known as the radius of convergence. Right? Whenever you have x minus the center is less than r, that number r is the radius of convergence. So here I have x minus the center less than 2. So radius of convergence is 2. All right, so that builds the basis for the interval. So far we've got x minus absolute value x minus 5 less than 2. So absolute value x minus 5 less than 2. Eliminate the absolute values by doing this. Well, either x minus 5 is bigger than negative, is bigger than negative 2, and it's less than positive 2. Add 5 to each part of this three-way inequality, and you have 3 less than x minus 5, or 3 less than x less than 7. Alright, so this is an interval of radius of length 4, so radius 2. R, right, which is equal to 4 in this case. So that's the interior of the interval of convergence. Of length 2 minus r. So now all that's left is to check the endpoints. Right? So we know the now we just need to check endpoints. Alright, so the endpoints are 3 and 7. Okay, well, let's check x equal to 3. Well, p of 3 is the sum n equals 1 to infinity, 1 over n times 2 to the n, 3 minus 2 to the n. 3 minus 2 to the n. What was the original function? 3 minus 5. 3 minus 5 to the n. 3 minus 5 to the n. So this is the sum. Please pay attention to the algebra here. N equals 1 to infinity. 1 over n, 2 to the n, minus 2 to the n. Minus 2 to the n is minus 1 to the n, 2 to the n, over n, 2 to the n. These guys cancel, and we have the sum, n equals 1 to infinity minus 1 to the n over n, which is the alternating harmonic series. By the alternating series test. So that's x equal to 3, x equal to 7. So P of 7 is the sum n equals 1 to infinity. 1 over n 2 to the n, 7 minus 5 to the n. So it's the sum n equals 1 to infinity. N 2 to the n, 7 minus 5 to the n is just 2 to the n. So those cancel. And this is the harmonic series, which diverges. All right, thus the interval of convergence for P of x equal to the sum n equals 0 to infinity, 1 over n 2 to the n, x minus 5 to the n, is 3 less than or equal to x less than 7. Okay, so we get the interior of the interval by the ratio test, and then the endpoints, just you have to check the endpoints. So you converge absolutely inside this interval, you diverge outside the interval, and on the boundary points you just have to check those individually. Okay? So a lot of different examples in the text like that. So I will leave that to the discussion later. The point of power series is really as follows. So, power series is a polynomial of infinite degree. And what we're going to find out is that most nice functions that we deal with, sine x, cosine x, polynomials themselves, e to the x, square root x, all these functions, they're all polynomials. Polynomials, well, polynomials of infinite degree. They all are representable using power series. Okay, so this is a really, really nice result. This is what we'll get in section 6.3, is that all these nice functions that we've been working with all along, they're all representable as power series. Okay, so in some sense, every nice function is a polynomial. So that's a pretty cool result. But so far, we already know one function represented as a power series. More examples later in chapter 6. Is that 1 over 1 minus x is the sum n equals 0 to infinity x to the n. Just this, very simple power series. 1 plus x squared plus x to the third plus, not for every x, right? Only for absolute value of x less than 1. Whenever you have x with absolute value of x less than 1, this power series converges absolutely, and it's equal to that function there. There's a lot of variations we can get. So this is one function represented as a power series. Okay, not for all x, but for some limited numbers of x's. But that's fine. But given just one function represented as a power series, you can do a lot of variations on that as well. So some variations. 1 over 1 plus x squared. Well, this is 1 over 1 minus x squared. So this is the sum, n equals 0 to infinity, minus x squared to the n. Right? 1 over 1 minus x is the sum x to the n. So all I did is I replaced x with minus x squared, and I get that. Instead of x to the n, it's minus x squared to the n. Alright, so this is equal to the sum, n equals 0 to infinity, minus 1 to the n, x to the 2n. For which x's? For all absolute value minus x squared less than 1. But absolute value of minus x squared is just absolute value of x squared. Well, if you're saying the absolute value of x squared is less than 1, I could just take the square root of that and you just get absolute value of x less than 1. So this function, which happens to be the derivative of arctangent x, by the way, right? This happens to be the derivative of arctangent x. This function has a power series representation right here. For all x whose absolute value is less than 1. Okay? So that power series, that function represented as a power series, just comes from the standard geometric series. But there's other variations you can take as well. 1 over, say, 4 minus x. Right? Factor out a quarter. Right, so this becomes 1 over x over 4, 1 minus x over 4, right? So as a power series, this is the sum, n equals 0 to infinity, right? X over 4 to the n. So this is 1/4, the sum, n equals 0 to infinity, 1/4 to the n, x to the n. And if you want, you can bring that 1/4 back in there. 1/4 to the n plus 1, x to the n. For all x with absolute value x over 4 right here, right? This thing inside the parentheses has to be less than 1. But what does that mean for x? Well, that's all x with absolute x less than 4. So absolute convergence for all x whose absolute value is less than, strictly less than 4. Equal to 4 with the geometric series, no, neither endpoint will converge, but we're mostly just interested in the interior at this point. Okay, other variations you can do would be something like this. Say like x to the third over 4 minus x. Alright, this is x to the third times 1 over 4 minus x. So this is x to the third, and we already have the power series for that. Right, so multiply this into here, sum n equals 0 to infinity, 1/4 to the n plus 1, x to the n plus 3. And again, that's for all x with absolute x less than 4. Right, when you take a power series and you multiply it by just some polynomial, it doesn't change the radius of convergence at all. Doesn't change the center, doesn't change the radius of convergence. Okay? So those are some functions that you can represent as power series. And we have, a lot more examples like that in the homework. All the examples in the homework for this section, they're all variations on the geometric series. So like the 2 examples I just did. So they'll all be just like that. Later on in sections 6.2, 6.3, and 6.4 will have power series representations for sine x, cosine x, square root x, arctangent x, natural log x, and all these other nice functions. Okay, so we'll talk about that next time, and that is the lecture for this section.